Definite integrals are going to play a huge role in the calculus that we're going to approach when we get to our applications of integrals. And we've seen already in an earlier video how to evaluate definite integrals using the limit definition. But for us to apply the definite integral in all of the other applications that are coming upon us, we really need a better way in order to evaluate the definite integral that will be actually more widespread for us to be able to use in those applications. This video is on something called the Fundamental Theorem of Calculus. And for this part of the Fundamental Theorem of Calculus, we're going to find a way to evaluate a definite integral using a link between our function and an antiderivative of that function. So let's get started. So here the Fundamental Theorem of Calculus, more commonly initialized as the FTC, says that if f is a continuous function on a closed interval, and this is small case f of x, that you're talking about the function being in your integrand, and if capital F is an antiderivative of small case f. So the case sensitivity of this theorem is really important to pay attention to. On that closed interval from a to b, then the definite integral from a to b of this small case f of x dx can be evaluated also by taking your antiderivative of that integrand, evaluated at the upper limit of integration, minus an antiderivative of that integrand evaluated at the lower endpoint of integration. So we're going to think about doing our work of our antiderivatives back when we were looking at those problems. And I'll put a link to several different videos looking at your indefinite integral for many different situations in the description of this video. But we have to think about, we're going to think about the problems in that sense. But then instead of having our answer be a family of functions where we have that family of functions with the plus c, we're actually going to run the upper limit of integration through an antiderivative minus the lower limit of integration through it. So we're actually going to get a number out for your definite integral instead of a family of functions. So when you think about this and think back to what we've already done, if you're talking about an antiderivative, which we also called an indefinite integral, notice there won't be any numbers on the lower part of your integral symbol and the upper part of your integral symbol. It's just going to be the integral symbol, your integrand, and then your differential. So this is what we already did in earlier videos, and it's an antiderivative, and it's a family of functions that we get. We had our expression and then plus the c, and we always had to remember that plus c. That's our indefinite integral. Now when we look at a definite integral, it's going to have a lot of the same structure, but it's going to have a number at the bottom of the integral symbol and a number at the top of the integral symbol. So that's going to be our definite integral, and this is a number answer that we're going to get out for it. And for the definite integral, you don't have to put the plus c, because this is where capital F is an antiderivative. So we can pick the antiderivative that has plus 0 as our constant term, and it will still work its way out. The other reason you can think through of why we don't need the plus c is when we run the upper limit of integration through our antiderivative, we would have the plus c here, but then we minus when we run the lower limit through, so minus that same c, the term would just cancel out anyway. So with your definite integral, you don't need the plus c. So let's look at some examples using our Fundamental Theorem of Calculus. Start with 3 examples of our definite integral questions and apply the Fundamental Theorem of Calculus to evaluate these instead of the limit definition. So for our first one, now remember again, this would be an indefinite integral, this is a definite integral. Indefinite integral, definite integral. Okay, Now, with our fundamental theorem of calculus, the first thing we want to do is actually think about it as if it were an indefinite integral. So what would we have done if we were looking at the indefinite integral of x to the third dx? Well, we would have noticed it was letter base to number power, and letter base to number power when we're integrating, as long as our number power is not -1, we add 1 to the exponent and we divide by that. So we have our base of x, 3 plus 1 is 4, and we divide by that. So we could either do that by putting it over 4 or putting a 1/4 in front of it. Now with the indefinite integral, we had to make sure we remember that plus c. But with the definite integral, instead of doing the plus c, we're going to evaluate this from 1 to 2. So to remind yourself or to show in that stage that you've already integrated, but you plugged your numbers in yet, after your antiderivative, you're going to put a vertical line with your lower limit of integration on the bottom and your upper limit of integration on the top. Now here's something that you want to remember. You need to plug in the upper limit of integration, then minus the lower limit of integration to get this value correct. So you plug in the 2 first, so it's 1/4 times 2 to the 4th, and then minus, because of what it is in the fundamental theorem of calculus formula for it, plug in your lower limit 1. 1/4 times 1 to the 4th. And then we just need to do the numerical work from there. So 2 to the 4th is 16, so I have 1/4 times 16 minus 1 to the 4th is 1, so minus 1/4 there. And then because I have the common denominator of 4 that I need to use, I'm going to think of this first term as 16/4, not 4. So I have 16/4 minus 1/4, which gives me 16 minus 1 is 15/4. So this 15/4 is the value for that definite integral. Let's look at the next one. This is the definite integral from 1 to 3 of x squared minus 5 dx. So remember, think about it in terms of your indefinite integral. Indefinite integrals we could do term by term, and with this I don't have an exponent up here. If it were a square or something, I would multiply that out, but this is just the term x squared minus the term 5. So letter base to number power when I'm integrating, as long as my number power is not -1, I add 1 to the exponent and divide by that. So that's 1/3 x to the 3rd, and then minus the indefinite integral of 5 with respect to x is 5x. Now that expression I'm going to evaluate from 1 to 3. So big difference here is instead of putting the plus c, we put the vertical line and then do our lower limit up to our upper limit. Plug in the upper limit first, minus plug in the lower limit. So this is 1/3 times 3 to the 3rd minus 5 times 3. And then subtract off of that. With more than one term, I have to remember to put parentheses around plugging in the 1. So open parentheses, plug in the 1, so it's 1/3 times 1 to the 3rd minus 5 times 1. So now remembering your order of operations, there's so much new going on that sometimes we glitch on the stuff we just thought we had just without even having to think about it, but just slow down and think your way through these steps. So follow your order of operations. So I have 1/3 times 27, and then minus 15, and then minus, I'll wait to get rid of my parentheses until I get rid of the work inside here. So I have 1 cubed is 1 times 1/3 is 1/3 minus 5 times 1 is minus 5. Now, because I do have a couple of places where I have a fraction of a denominator with 3, I'm going to leave those fractions a little bit and see what pans out from here. So I have 27/3 minus 15 minus 1/3 plus 5. And I leave this 27/3 instead of going to 9, just because I also saw I was going to minus 1/3 here and to kind of ease our calculations. So thinking about how I can combine these, I have 27/3 minus 1/3, well, that's 26/3. And then I have a minus 15 and a plus 5. So those combined give me a negative 10. And it just helps me a little bit get my common denominator. Then I have 26/3 minus 30/3. And 26/3 minus 30/3 is a negative 4/3. So this definite integral is my negative 4/3. And certainly there's a lot of different ways you could have handled the arithmetic part of it. I just like to work with the numbers that are just more compatible to put together and then finish it off on the end. But the main thing is, with however you did that arithmetic, following your order of operations in the middle here, that you came up with the negative 4/3. Okay, let's look at the next one. This is the definite integral from 1 to 4 of 5 times the square root of x dx. Well, remember with definite integral properties, I can pull the 5 out, and I can also do that when I think about it as an indefinite integral. So I pull the factor of 5 out, still the integral from 1 to 4. I'm going to write the square root of x as x to the 1/2 dx. So then I have my 5 times, and then think now you're going to integrate it as if it's an indefinite integral, letter base to number power. As long as my number power is not negative 1, I add 1 to the exponent and I divide by that. So 1/2 plus 1 is 3/2. And when I divide by 3/2, it is multiplying by 2/3. But instead of doing the plus c, we're going to have our vertical line and evaluate from 1 to 4. Now this 5 that was already out in front, you're going to multiply that to the 2/3. So this gives me 10/3 x to the 3/2 evaluated from 1 to 4. Now put in the 4 minus put in the 1. So I have 10/3 times 4 to the 3/2 minus 10/3 times 1 to the 3/2. Now we want to remember what we have when we have our fractional exponents. Remember, for fractional exponents, the denominator is the index, the numerator is the power. So this is 10/3 times, the denominator is 2, so the radical index is 2 for a square root. So that's a square root of 4, and then that square root of 4 answer is going to be raised to the 3rd power. And then minus 10/3 times the square root of 1 cubed. So square root of 4 is 2. 2 cubed is 8. So I have 10/3 times 8 minus square root of 1 is 1, 1 cubed is 1, so minus 10/3. So that's 80/3 minus 10/3 gives me 70/3. So this definite integral is 70/3.